Nice to meet you. I'm Khadar Choktai and you're watching my YouTube channel School of Advanced Chemistry. Today I'm going to discuss Kp, equilibrium constant in terms of partial pressure for AS chemistry students. Let's talk about Kp. Kp stands for equilibrium constant in terms of partial pressure. Kp. During the course of a chemical reaction, that is a reversible reaction, when it is happening in a sealed container, a stage comes that is said to be dynamic equilibrium. At the stage of dynamic equilibrium, when the speed of forward reaction is equal to the speed of reverse reaction. At this stage, the ratio of the pressure of the gases present on the left hand side with respect to the pressure of or the partial pressure of the gases present on the right hand side. So basically this Kp is the ratio of the pressure of the gases present on both sides. I mean, once again, capital K is equilibrium constant in terms of partial pressure. So this Kp is the ratio between the pressure of the species present on the right hand side of the equation. If they are gases, for example, in this case NH3, raised to power this number, this coefficient raised to power 2, divided by the pressure, partial pressure of the gases present on the left hand side, of the equation. In this case, the nitrogen is gas, so I'm going to put nitrogen and 2. Its coefficient is equal to 1. I mean, mole is equal to 1, so it will be its power 1. Then multiply by the next reactant that is also gaseous. So the pressure of hydrogen and its power is equal to 3 because 3 mole of hydrogens are being used. Kp is equal to the pressure of ammonia divided by the pressure of nitrogen into pressure of hydrogen. This expression is said to be the expression of Kp for this given reaction, for this Haber process. So this is the way to write the expression of Kp. What is the Kp? Kp is the ratio of the pressure of the gases present on the right hand side to the pressure of the gases present on the left hand side. So this is the way how we can write the basically expression of Kp, or equilibrium constant in terms of partial pressure. Now the next thing is, how can we find the unit? The units are basically calculated from the expression. So you can see that for example, in this case, the pressure or the total pressure, you can say, that is being measured in Pascal. So in terms of Pascal, I'm going to write once again this expression. I'm going to change this expression in terms of Pascal. So here there's a Pascal square divided by Pascal multiply by Pascal cube. So overall, here is Pascal square divided by, here is Pascal raised to power 4. So what is the overall answer? That is equal to 1 over Pascal square. So I can write Pascal minus 2. That is said to be the unit of this Kp. It may be having no unit, but at the moment its unit is equal to Pascal raised to power minus 2. Now, how to calculate the Kp numerically if the data is given? Here are basically almost overall 5 to 6 steps. Number 1, if I'm having the initial mole, step number 1, you will use initial mole. For example, let's suppose I'm having 2 mole of nitrogen in a sealed container, and these are allowed to react with same 2 mole of hydrogen to make ammonia. At the moment, there is no mole of ammonia, so I'm putting 0 over here. Initial moles of nitrogen is equal to 2, initial mole of hydrogen is equal to 2, and initial mole of NH3 is equal to 0 at the moment. After some time, after enough time, I mean, when the equilibrium has been reached, as you know, a time will come when the rate of forward reaction will be equal to the rate of reverse reaction. So this stage is said to be dynamic equilibrium, the stage of dynamic equilibrium. So what is happening, or what are the moles at dynamic equilibrium? How to write this expression at the dynamic equilibrium? I can write this expression 2 minus y. I mean, here is 1. I can write 1y. Y is the mole of change that is going to decrease, mole of decrease of nitrogen, and comma. This time I'm going to mark comma over here. And what is the initial mole of hydrogen? 2. Again, hydrogen is also going to decrease in concentration in mole. So it's 2 minus y. I mean, y is the mole of change overall. Y is the mole of decrease from hydrogen in term of, or with respect to, in the multiple of this mole 3. So hydrogen will change its mole, will decrease its mole by the multiple of 3. Nitrogen will change its mole by the multiple of 1, and so on. Goes to 0 plus. There is, increment, or you can say there is increasing the mole, and there will be again with respect to this mole. So there will be, let's suppose there is addition of y mole in term of 2, or with respect to 2y. Now, for example, let's suppose I'm having the value of, or I have checked the value of ammonia at the stage of dynamic equilibrium. If the moles of ammonia is given to me at the stage of dynamic equilibrium, let's suppose this mole is equal to, let's suppose the mole of ammonia is equal to 1. So if NH3 mole, if mole of NH3 is equal to 1, so it means that 2y is equal to 1 and y will be equal to 1 by 2. I mean, this value will be given to you. So, you can find the value of y. Find the value of y, that is 1 by 2. So, put the value y 1 by 2, 1 by 2, 1 by 2 over here. Now, that will be the numerical answer of the moles at equilibrium. So, what will be this answer? 2 minus 1 by 2, that is 1.5, comma. What is this answer? 2 minus here 1 by 2, that is 3 by 2, 1.5. Here is overall answer is 2.5. Goes to, and obviously there will be 2 into 1 by 2 is equal to 1. So these are the numerical answer of the moles of remaining nitrogen at the stage of dynamic equilibrium, remaining mole of hydrogen at the stage of dynamic equilibrium, and the mole of ammonia that has been formed at the time of dynamic equilibrium. So these are the moles. Now the next step is to find the total moles. Total mole is quite simple, is class 2 mathematics. 1.5 is the mole of nitrogen plus 0.5 is the mole of hydrogen plus, and ammonia mole is equal to 1. So overall mole is equal to 3, that is equal to total mole. So total mole is equal to 3. These were the mole at equilibrium, these were the initial mole, and so on. Now next step, or the next thing, is to find the mole fraction. How to find the mole fraction? The mole of any gas, of each gas divided by total mole. So what is the mole fraction of nitrogen? Mole fraction of nitrogen will be 1.5 divided by total mole. Right. What is the mole fraction of hydrogen? It will be 0.5 divided by total mole. And what is the mole fraction of NH3? That is 1, its own mole, divided by total mole. So these numbers are said to be the mole fraction. Next thing is to find the partial pressure. And how to find the partial pressure? Basically, that is mole fraction of nitrogen multiplied by Pt. Same is the case mole fraction. This is a simple notation of mole fraction. Mole fraction of hydrogen multiplied by Pt, Pt being total pressure. Same is the case with ammonia, mole fraction of NH3 gas multiplied by Pt. So only gases, as you know, only gases are present over here. all gases are present and all gases are chosen in Kp. So these all are having now the different pressures, and we are having their partial pressure. They may have same pressure, they may have different pressure, but at the moment we have calculated their partial pressure. So what is the partial pressure? Let's suppose, once again, I'm going to suppose that the total pressure of the container, of the sealed container in which this is happening, this whole reaction is happening, let's suppose is overall it is 900 kilopascal. For example, its total pressure is equal to 900 kilopascal. So what is the partial pressure of nitrogen? In this case, mole fraction is equal to 1.5 over 3 into Pt, and Pt is equal to 900. So same for hydrogen, 0.5 over 3 multiplied by Pt, and Pt is equal to 900 kilopascal. Ammonia, what is the basically ammonia? Ammonia is equal to 1 by 3 into Pt, and Pt is equal to 900. So what is the answer basically? What is the answer? That is equal to, this one, 450, and that is equal to 150 partial pressure, and that is equal to 300. Just keep in mind, you can check your answer once again. If I'm going to add all these values, and the overall answer must be equal to 900. 450 plus 150 plus 300 must be equal to the total pressure, that is 900. Yes, it's 900. Now the last one stage is to put the values, these pressure values of this pressure into the Kp expression. So what is the expression of Kp for this reaction? Once again, it was the pressure raised to power 2 for NH3, that is written in small brackets, pressure of nitrogen, you can write the small bracket if you want to do, yes, and pressure raised to power cube, raised to power 3 for hydrogen. So what is the answer of this ammonia partial pressure? That is equal to 300. So 300 raised to power 2 divided by what is the partial pressure of nitrogen? 450 raised to power 1 multiply by what is this one, hydrogen's partial pressure, that is equal to 150 n raised to power 3, and here it will be the value of overall Kp. So these are the basic step whenever your initial moles are given. If you're starting from the initial mole, then you will start from step number 1. If you are having the mole at equilibrium, then you will start from this step number 2. If you're having partial pressure, let's suppose, then you will start from this 5th step, or you can say the last step. So whatsoever is the given, the question will be molded and question will be designed according to the given situation, according to the given data, and so on. Now, the next thing is Kc and Kp answer will be changed by change in temperature only. By changing the pressure, by changing the concentration, by changing the surface area, by adding the catalyst, the answer of Kc, Kp will not be changed. The answer of Kc and Kp will be changed only if you are changing the temperature, and it is going to depend upon the nature of the reaction. If reaction is exothermic, then low temperature will increase the value of Kp. So Kp will be increased if the temperature is low, if the reaction is exothermic. In case of endothermic, high temperature will increase the value of Kp, and reverse is also true. So low temperature will favor the exothermic reaction. As you know, high temperature favors the endothermic reaction. When the temperature is favoring the forward reaction, then obviously the answer of Kp will change. If the temperature conditions is not favoring the forward reaction, then obviously the answer of Kp will be decreased. Now come toward this example. At temperature above 1500 Kelvin, HCl will decompose. A sample of 0.3 mole of HCl decomposed in a sealed container, the resulting equilibrium mixture has found to contain 1.5 into 10 to the power minus 2 mole of Cl2. Calculate the amount in mole of H2 and HCl present in the equilibrium mixture. Now we are having this equation. H2HCl goes to Cl2 plus H2 and so on, and we are starting from the initial mole of HCl. So I'm going to start from the very beginning. Initially, what is the mole of HCl? 0.3. There is initially no mole of Cl2, there is no mole of hydrogen. Now what is happening at the stage of equilibrium? It will be 0.3 minus 2y goes to 0 plus y for Cl2 and same 0 plus y for hydrogen. Now he has announced that at the stage of dynamic equilibrium mixture being at the stage of dynamic equilibrium, the value of mole of Cl2 is lying over here. So it means that this is the y. 0 plus y, I mean the y is equal to this one. The mole of Cl2 is y, so the actual mole is equal to this one. So it means that y is equal to 1.5 into 10 raised to power minus 2 is equal to y. So put y is equal to 1.5 into 10 raised to power minus 2 where there is a y, and then we will get the answer. So 0.3 minus 2 into 1.5 into 10 raised to power minus 2 goes to, that is 1.5 into 10 raised to power minus 2, and same is the case, I mean, for hydrogen. So we have find the value of hydrogen as well. The same answer is for hydrogen. It will be 1.5 into 10 raised to power minus 2 moles. What is the value of HCl, remaining HCl, that is over here? I mean 0.3 minus, this answer will be equal to 3 into 10 raised to power minus 2, and it will be equal to 0.5. The mole of HCl is equal to 0.27. 0.27. So this is the part 1 of this question. Now he is asking to calculate the mole fraction of each gases at the equilibrium. I'm going to find the total number of mole. Total moles. Total mole is equal to 0.27 for HCl. This mole is for HCl plus the mole of hydrogen, that is 0.015 plus the mole of hydrogen, that is same 0.015. So in case of mole fraction of HCl, that is going to be equal to 0.9. 0.27 divided by this whole answer, that is equal to, so the total mole is equal to 3 by 10. And what is the mole fraction of this HCl? 0.27 divided by 3 over 10, or I can write 10 over here, I mean, and that is equal to 3 9s are 27. So total mole is equal to 0.9. 0.9 into 10, that is equal to 0.9. So this is the mole fraction of HCl, 0.9. What is the hydrogen mole fraction of hydrogen? That is 0.015 divided by 3 over 10. I mean, I can write 10 over here, and that is equal to 0.05 into 10. So 0.05 into 10, that is equal to 0.5. 0.05. And same is for Cl2, that is also 0.05. So these are the answer of the mole fractions of HCl, H2, Cl2, and so on. Now come towards the next part, that is the D. In this case, the mole fraction of HCl is over here is given. I mean, in another experiment, under the different conditions, the equilibrium mixture was produced, mole fraction with each of as shown over here. So HCl mole fraction is 0.88, H2 mole fraction is 0.06, and Cl2 mole fraction is 0.06. Part 1, write the expression of the equilibrium constant Kp. What is the Kp? Kp is equal to the partial pressure of the gases present on the right hand side, only gases. So partial pressure of hydrogen raised to power 1 multiplied by the partial pressure of Cl2 raised to power 1 divided by the partial pressure of HCl raised to power 2. I can put try 2 over here or 2 over here. It's one and same thing. So this is the expression of Kp. Now in next part, explain why the total mole of the system doesn't need to be known for Kp to calculate Kp to be calculated for this experiment. I mean, why the total pressure of the system doesn't need to be known for the calculation of Kp. The basic reason is, you can see it over here, basically overall pressure is same. In numerator and in denominator, both are having the same pressure square basically. So equal number of mole of the gases on the either side are present. Overall, 2 mole of gases are over here, 2 moles are lying over here. So because of there are same moles, so the pressures are there is same pressure on the both side. So equal pressure will cancel out and there is no need to write the pressure. Same mole of gas on each side, same moles of gases on each side. Pressure will cancel out. Pressure will cancel out. And calculate the value of Kp for this experiment. So what is the expression you know? Is what Kp is equal to the partial pressure of hydrogen multiplied by partial pressure of Cl2 divided by the partial pressure square for HCl. So what is the answer? What is the value of partial pressure of hydrogen? 0.06, 0.06. So 0.06 for hydrogen multiplied by 0.06 for Cl2 divided by what is the value of HCl? 0.88. So just 0.88. I'm putting the mole fraction rather than the partial pressure. There is no need to change them into the partial pressure because there is no involvement of the partial pressure over here. So that's why I'm not using the partial pressure. I'm using the same values of mole fraction over here. So what is the answer? 0.06 multiplied by 0.06 and divided by 0.88, and the answer is 4 into 10 to the power minus 3, or 4 into 10 to the power minus 3. Yes, that is equal to 4 into 10 to the power minus 3 is the answer of Kp. Now come toward the next question. In another question, another equilibrium mixture formed from the different starting amount of SO2 and O2. The partial pressure of SO2, O2, and SO3 are shown over here. Now this time he is asking to start from the partial pressure, and partial pressures of each and every mole is given over here. Write the expression for the equilibrium constant Kp for the production of SO3 from SO2 and O2. Let's 2 mole of SO2 plus 1 mole of oxygen goes to 2 mole of SO3. This is the equation, for example. So the Kp will be according to this equation. If these moles have been changed, then Kp will be changed. dependent on these numbers. If you are going to raise their number, even you are not changing the stoichiometric ratio, the ratio is same, but if you are changing the number, you are increasing or decreasing the number, then expression will obviously change. But the main thing is your answer of Kp will be changed. So answer of KCKP is highly dependent on these values of the moles. So according to this equation, this recent equation, this reaction, I'm going to write the expression of Kp with respect to this equation. So partial pressure on the species present on the right hand side, that is SO3. So SO3 raised to power 2 divided by pressure of SO2 raised to power 2 multiply by partial pressure of O2. So this is the overall true expression of Kp for this said reaction. Now he's asking to calculate the value of Kp for this reaction and state the units as well. So what is the partial pressure of SO3 first of all? This is this one. So 9.1 into 10 raised to power 4 raised to power 2 divided by what is the partial pressure of SO2? This one 8.42 into 10 raised to power 2 raised to power 2 multiply by the partial pressure of oxygen, that is 6.00 into 10 raised to power 4 Pascal. These all are the basically Pascal. So what is the answer of Kp? That is 0.194 and is 0.194. What are the units basically? And you can see that two pressure square over here. I mean pressure square over here. Here's pressure square multiplied by the pressure. So they will be cancelled out. There is only 1 over P and the pressure is given in Pascal. So 1 over Pascal, I mean, you can write Pascal inverse Pa minus 1. Here are the units. Now come toward the next question. 2 moles of sulfur dioxide and 2 moles of oxygen were put in a flask and left to reach equilibrium. At equilibrium, the pressure is in the flask was 2 into 10 to the power 5 Pascal and the mixture contains 1.8 mole of sulfur dioxide. Calculate the Kp, include the units for 5 marks. So first of all, I'm going to write the equation. Once again, 2 mole of SO2 plus 1 mole of oxygen goes to 2 mole of SO3. What are the initial mole of SO2? That is equal to 2 mole. So 2 mole of SO2, same 2 mole of oxygen. They were allowed to mix. So reaction is going to start from the beginning, from first step. So 2, 2, and it's equal to 0. What is the next step? 2 minus y. Which one y? I mean 2y. 2 minus 2y. This SO2 will change with respect to 2y with the multiple of 2. And oxygen will change with respect to 1y. 2 minus 1. Here is a 1. So it will be 2 minus 1y. Goes to double arrow, I mean 0 plus this SO3 will change, will increase with respect to with a multiple of 2. So it will be 2y. Now he is saying that at the stage of dynamic equilibrium, SO3 is equal to 1.8. So SO3 in my equation, SO3 is equal to 2y. Here SO3 sulfur dioxide is equal to 1.8. So 2y is equal to 1.8 and y is equal to 1.8 over 2. I mean it's equal to 0.9. So put 0.9 over here where there is y. So what will be the answer in first step? 2 minus 2 into 0.9, that is 1.8. So 2 minus 1.8, that is equal to 0.2. 0.2, comma. What will be the answer over here? 2 minus 0.9, that is equal to 1.1. 1.1 goes to, obviously it will be equal to 1.8. So the next step is to find the total number of mole. So 0.2 plus 1.1 plus 1.8, that is equal to 3.1 if I'm not wrong. That is equal to 3.1. 3.1 is equal to total mole. What is the next stage or next step? That is to find the mole fraction. So what is the mole fraction of SO2? Mole fraction of SO2 is equal to mole of SO2 is equal to 0.2 mole divided by what is the total mole? 3.1. What is the mole fraction of O2? 1.1 is the mole of O2 divided by total mole, that is 3.1. And what is the mole fraction of SO3? That is the mole of SO3 is equal to 1.8 at the stage of dynamic equilibrium. And what is the total mole? Total mole is equal to 3.1. So these numbers are called mole fraction. Now come to the last step. If I'm going to multiply these number of mole with the total pressure, 2 into 10 raised to power 5 Pascal, this mole fraction multiplied by Pt, 2 into 10 raised to power 5, and same is the case 2 into 10 raised to power 5. So these answer have changed into partial pressure. So now there will be the answer of the partial pressure of SO2. I mean 0.2 multiplied by 2 into 10 raised to power 5 and divided by 3.1, and the answer is 12903. What is the partial pressure of this oxygen? That is 1.1 multiplied by 2 into 10 raised to power 5 and divided by 3.1, and the answer is 70967. These all are said to be partial pressure. Partial pressure. And what is the partial pressure of SO3 at equilibrium? That is 1.8 multiplied by 2 into 10 raised to power 5 and divided by 3.1, and the answer is 116129. Now it's time to put this value into the Kp. The expression of Kp is equal to pressure of SO3 square divided by the pressure of SO2 square multiplied by pressure of oxygen. So what is the pressure of SO3? That is 116129 square, right? And it's divided by the pressure of SO2, that is 12903 square multiplied by the pressure of partial pressure of oxygen, 70967. So this will give you the answer of Kp. So the overall answer of the Kp is equal to, if I'm not wrong, that is 1.14 into 10 raised to power minus 3. Now what are the units? As you have seen that pressure square. So there is only one pressure left in denominator. So it is 1 over P again once again. And the pressure unit is Pascal. So again it will be 1 over Pascal, and there are the units. Now come toward the next one. Part B. Nitrogen dioxide exists in equilibrium with dinitrogen tetroxide. 2 mole of dinitrogen tetroxide was sealed in a container. This time examiner is asking to start the reaction from this one, from the right hand side, and initial mole of this is equal to 2. So reaction is moving in backward direction. After equilibrium had been established, the total pressure is equal to 140 kilopascal, that is total pressure PT. I mean, the mixture of gases contain 1.84 mole of dinitrogen tetroxide. I mean, the remaining N2O4 is equal to 1.84. So again, it is confirmed that the reaction is moving in reverse direction. Now he is asking to find the value of Kp. Once again, if although the reaction is moving in a reverse way, but the expression of Kp will be written with respect to this equation from the given equation. I mean, what is the Kp? Kp is equal to the pressure of species present on the right hand side, that is N2O4. As I told you, reaction is moving in a reverse direction, but we are not concerned with the direction of reaction whenever we are going to write the expression of Kp. The Kp expression of Kp is written with respect to from or that is dependent on the equation given for that chemical reaction. So, with respect to this equation, the expression is written with respect to this equation. So, pressure of N2O4 divided by pressure of NO2, that is raised to power 2 because of this 2 mole. Now he's asking to find the number of mole of NO2 present at equilibrium. I'm going to write once again. 2 mole of NO2 goes to N2O4. I'm starting from here. 2 mole, initially there is 0 mole, and this N2O4 is going to decrease itself. So 2N2Y, I mean there is a 1 mole, so 1Y, and it will be 0 plus 2Y, 0 plus 2Y. Now this is the condition at dynamic equilibrium. So the mole of N2O4 is equal to 2 minus Y. The mole of NO2 is equal to 2Y at the stage of dynamic equilibrium. He is saying that we are having 1.84 mole remaining for this dinitrogen tetroxide. So remaining mole, I mean 2 minus Y is the remaining mole in this equation for N2O4, and according to the examiner's report, 1.84 is the remaining mole. So 1.84 is equal to 2 minus Y, and 2 minus 1.84 is equal to Y. And what is the answer? 1.84. 1.84. So 2 minus 1.84 is equal to, that is equal to 0.16. So Y is equal to 0.16. So put Y over here. So 2 into 0.16 goes to obviously 2 minus 0.16, that is equal to 1.84. So what is the answer of mole of NO2? 0.16 into 2, that is 0.32. So 0.32 moles of NO2 will be present at equilibrium. Calculate the total number of mole of the gases present at equilibrium and hence mole fraction of the each gases. You know, I mean the mole of N2O4 is equal to this one, N2O4, and the mole of NO2 is equal to this one. So what is the total number of mole? 1.84 plus 0.32, and the answer is 2.16. So the total mole is equal to 2.16. Now, what is the mole fraction? Mole fraction of NO2. Its mole is equal to 0.32 divided by 2.16. What is the mole fraction of N2O4? N2O4 is equal to 1.84 is the mole of N2O4. Total mole is equal to 2.16. So what is the answer? 0.32 divided by 2.16, and the answer is 0.148. Now 1.84 divided by 2.16, and the answer is 0.851. So these are the basically mole fractions, mole fraction of NO2, mole fraction of N2O4, and so on. Now the next segment is calculate the partial pressure of each gas, and we have seen that 1 mole fraction is equal to 0.148. So partial pressure of NO2 is equal to 0.148 into total pressure. What is the value of total pressure? The value of total pressure is equal to 140 kilopascal. So I'm multiplying by 140. So 0.148 multiplied by 140, and answer is equal to 20.72. What is the partial pressure of N2O4? That is 0.851 multiplied by again 140, and the answer is 119.14. So these are the partial pressure. In next segment, he is asking to find the value of Kp in three significant figures, and what is the expression of Kp. Kp is equal to, you know that, the partial pressure of N2O4 divided by the partial pressure of NO2 square. So N2O4 is 119.14 divided by 20.72 square. And the answer of Kp is equal to 0.277. And the unit is once again pressure is over here, here is pressure square. So definitely 1 over pressure, and again the pressure is in Pascal. So it will be 1 over Pascal and so on. That's all about this topic, this KP. Please subscribe my channel, hit the bell icon and share it with your friends. Thank you. Thank you very much. Have a nice day.